Question number 27. A playground merry-go-round is at rest, pivoted about a frictional axis. A child of mass m runs along the path tangential to the rim with a speed v and jumps on the merry-go-round. If r is the radius of the merry-go-round and I is its moment of inertia, then the angular velocity of the merry-go-round and the child is. So here this is a merry-go-round. If you take now a child is running in this direction because he has to run tangential and circle. So the velocity of the child is v, the mass of the child is m, then it is moving in a circular track of radius r because the radius of the merry-go-round or the child will be same, so it is mvr. So using conservation of angular momentum, the initial momentum of the kid, mass of the kid into the velocity to radius, this is the initial angular momentum mvr, that is should be equal to the angular momentum of the kid when it is the this is rotating with an angular velocity omega. Let us say after the kid is getting into the merry-go-round, the merry-go-round rotates with an angular velocity omega. In that case, it is a m r square omega is the angular momentum when it is rotating, plus the moment of inertia of the merry-go-round is I, its angular velocity omega, then I omega is the angular momentum of the rotating merry-go-round. So the initial momentum of the kid should be equal to the final angular momentum of the kid and this and the merry-go-round. We want to calculate the omega, isn't it? So mvr is equal to m r square omega. Omega can be taken outside, so we'll remove the omega from here. Omega equal to mr square plus I is omega. So what is omega? Then omega from this equation is mvr divided by mr square plus I. So it is mvr by mr square. I is the correct answer for the angular velocity. So correct choice is answer is A. mvr divided by mr square plus I is the correct choice.